A fairly significant barrier of entry to the open source drone ecosystem is the cost of hardware required to develop open source drone software. The relatively standard entry-level Pixhawk 4 flight controller costs around $100 alone. An X500 development kit from Halibro, which we graciously received via a sponsorship a few months ago, normally costs around $500. For comparison, a comparable proprietary DJI Tello drone costs around $100 at a retail price. For many would-be open-source drone software contributors, this relatively high cost poses a high barrier of entry to the open-source community. Beginners have difficulty justifying paying 5 times as much to learn to develop a drone. Cost becomes a major issue in other applications as well. Large-scale swarms are another example. Our club, AmadorUAVs, has developed an open-source, low-cost flying platform to address these issues. Dubbed Project Mikro, the project began as a thought experiment our members discussed on the way home from school way back in 2019. Would it be possible to build a drone capable of semi-autonomous flight for under $50? We thought it should be possible to build one, but at the time, our lack of experience meant that we weren't really able to pursue it, so unfortunately the project never took off.
Fast forward to this summer. We had several years of drone experience under our belts, and as the SUAS competition we were competing in had been cancelled due to COVID-19, we had the free time to pursue side projects as well. So once we began looking at the feasibility of building an affordable micro-sized drone for experimentation, learning, and swarm applications. After deliberation and consideration of factors such as crash survivability, weight, flexibility, and, most importantly, cost, we settled on brush design, utilizing 65mm props, a 3D printed frame, and 8520 motors to generate around 160 grams of thrust. The entire system would run on a 1-cell battery at 3.7 volts. The flight controller, we decided, would be entirely custom designed and manufactured. This drone would definitely not be lifting any heavy payloads, but what it could do is act as a small, convenient experimentation platform for testing path planning and swarm behavior, for the low price of only $45. This low cost, coupled with custom manufacturing, means that beginners can easily get their start in the drone world. Designing a custom frame was one of the various challenges we needed to solve in the design. Our frame needed to be as light as possible, while also being sturdy enough to survive the regular crash. Tasked with a nearly impossible weight limit of 10 grams, we made it work by using a regular X frame design, opting for a simple friction/glue fit for the motors. By integrating the flight controller PCB into the frame design, the shallow basket component, the PCB partially helps distribute the force on the drone, making it more resistant to crashes. We also extensively utilized static finite element analysis, or FEE, to stimulate how the frame would respond to forces, allowing us to compensate for stress points, optimize frame rate, and build a stronger and lighter frame overall. The final product is an incredibly lightweight, simple frame that is not only easy to manufacture and build, it is also incredibly strong and micro-sized.
The flight controller is likely the most important part of this project. Flight controllers in general are expensive. Even less powerful flight controllers based on older STM32F3 microcontrollers can cost upwards of $25. These flight controllers can't even run PX4. So we knew from the beginning that if we wanted to build a PX4 capable drone, we would need to go completely custom for our flight controller. After considering cost and performance, we selected the ESP32 IoT microcontroller for our first prototype. It had several key features that were important to us. The first was its price. In a year where semiconductor shortages have driven many microcontrollers out of stock or to 10x markups, ESP32 modules were still readily available for around $4. The second was its performance. The ESP32 was dual core. With a 240 MHz clock speed, 512 kilobytes of RAM, and 2 megabytes of flash, it had more than enough processing power to run PX4. Another key advantage was that there was already a community-supported Autopilot project to support the chip. That meant we could get up and testing on a MAVLink-enabled Autopilot even before we got to porting PX4. That's not to say that it was without its disadvantages. Power draw and footprint size were a concern, as was the rather limited I/O. However, the advantages outweighed the disadvantages, and so we chose it to form the heart of our new flight controller. Second was the sensor suite. We originally selected the legacy MPU 9250 9-axis IMU unit, combined with the BMP-280 magnetometer. This was done largely out of cost concerns and in order to take advantage of what had already been tested with the Autopilot fork. As the MQ-920 is a deprecated chip, we resorted to using the cheap GY91 breakout board to act as a sensor suite. Testing confirmed that the resulting solution is capable of giving a reasonably accurate position and attitude estimate. However, this solution is not ideal for several reasons. The MQ-920 and BMP-280 are both old sensors, and the usage of a breakout board adds weight to a very constrained drone. Work has already begun on a second version of the sensor suite, a new version of the flight controller, based on the ICM-20-789 7-axis IMU and barometer combination, and the relatively new MMC-5633NJ magnetometer, which will offer more accurate attitude and altitude estimates for a similar price, is currently being designed at our club, although this version is not yet ready for presentation. Over the course of a few weeks, after designing the flight controller and frame from scratch, we assembled the final product together. The final prototype, Project Mikro V1.1, features an 800 mAh battery, a 3D printed frame, 4 8/520 motors, and 65mm props, and a custom ESP32 based flight controller with wireless telemetry. The total cost of an entire drone, from motors to batteries to sensors to board, is $41.19, proving the viability of a low-cost experimentation platform for open-source autopilots. Moving forward, we'll aim to replace the obsolete sensor suite with a more modern one, integrated into the flight controller, make optimizations to flight performance, and create an expandable board stacking standard to allow for breakout boards to easily be attached. We look forward to where Project Mikro is going, and we hope you stick along with us for the ride.